So, here is the next theorem, important theorem that we are going to show. If G has no negative cycle, there is an edge uv such that delta v equals delta u plus wuv. How do we prove this? Again, the proof is very typical of the kind of proofs that we let P be a shortest path from S to V and let uv be its last edge. So, from S this is the shortest path from S to V. Okay. Let Q be the part of P from S to U. This part is Q from S to U. Therefore, P equal to Q plus UV. Q, add the edge UV, you get P. Therefore, weight of P equal to weight of Q plus weight of UV. If we prove that Q is the shortest path from S to V, okay. Suppose you prove that Q is the shortest path, weight of P equal to weight of Q plus weight of UV. If we prove Q is a shortest path from S to U, if, this is an if, we are still to do that. If we prove this is the shortest path from S to U, then weight of Q equal to delta U and delta V, which is equal to weight of P, because P is the shortest path, which is equal to WQ plus weight of UV, and this is delta U plus weight of UV. So, we would have proved our theorem if we prove that Q is a shortest path. Okay. We prove that Q is a shortest path by a contradiction, assuming that Q is not the shortest path. What will be the contradiction we would get? Okay. Very typical of what is known as cut and paste argument, and let us, this is P, U, V, this is Q. If Q is not shortest, let us consider Q dash as a shortest path from S to V. If Q is not a shortest path, let Q dash be a shortest path from S to U. Therefore, weight of Q dash is less than weight of q. Now consider the following cases: q dash does not contain V, then q dash plus uv is a path from S to V. You can see the figure, q dash goes from S to U and U to V is added. So, it is a path from S to V, and weight of q dash plus uv is equal to weight of q dash plus weight of q dash plus weight of uv, but weight of q dash is weight of q plus weight of uv, which is equal to weight of p, which is equal to delta v. So, I have a path from S to V, this is the path from S to V, its weight is smaller than delta v, that is q dash plus uv is a path from S to V with weight smaller than weight of P. P is the shortest path. You cannot have a path shorter than that. This is a contradiction. Thus, q dash must pass through V. Therefore, the scenario is like this: I have S, this is Q, this is UV, the whole thing is P. I have a shortest path Q dash must pass through V. So, Q dash is like this. This is how Q dash is. Okay? Q dash is passing through V now. If Q dash does not pass through V, we have a contradiction. So, that forces us to consider that Q dash must pass through V. Therefore, Q dash plus UV is a walk from S to V, because already V is there and again you are visiting V. Therefore, the vertex V is occurring twice in Q plus UV dash. Therefore, it is not a path, it is a walk. Right. However, in any walk, right, we can remove the cycles and reduce the weight, because G is non-negative, no cycle in G, right, G has no negative cycles, G has no negative cycles. You can see that Q plus UV is a walk, Q dash plus UV is a walk, weight of q dash plus uv, weight of q dash plus weight of uv is less than weight of q plus weight of uv, which is equal to weight of p. But q dash plus uv is a walk. This walk, right, has a path to v and a cycle from v to u, right, cycle from v to u to v. So, you remove the weight, you remove that cycle. When we remove the cycle v part of q dash u v, you get a path s to v, it is a part of q dash. Now, you write q dash, plus uv as q dash going from s to v plus a cycle c. What is that cycle? Q dash from v to u plus the edge u v. This is a cycle. Okay. Q dash I write in two parts, it is passing through v. Okay. Let us write this. Q dash is passing through v, split q dash at v. Therefore, q dash equal to q dash from s to v plus q dash from v to u. There are two parts. Q dash is going from s to u. Since v is a part of the path, I split at v, I get two paths. Therefore, q dash plus the edge u v is q dash s v plus q dash v u plus edge u v. This is a cycle. This is a cycle. That cycle. Q dash from s to u, q dash from v to u and u to v, it completes that cycle. This cycle is over here. So, I can drop because all cycles have got positive weight. Therefore, weight of q dash plus u v is greater than or equal to q dash s v, because the cycles have non-negative weight. There is no negative cycle. So, any cycle will have either a 0 weight or positive weight. You can drop that, it becomes an inequality. This is a path from s to v, right. This is the path from s to v. Therefore, q dash s v is less than or equal to w q dash plus u v, which is less than w p. That means I have a path with smaller weight. Weight of q dash plus weight of q dash SV is less than or equal to weight of q dash UV, which is less than WB. This again a contradiction. You cannot have a path with a smaller weight. Therefore, this contradicts the minimality of P. P is the shortest path, but I have a part of q dash from S to V, it has a smaller weight, impossible, right. So, this clean proof shows that you cannot have a path shorter than q. This implies such a path q dash from S to U with weight smaller than q cannot exist. This implies q is a shortest path from S to U, which in turn implies weight of q equal to delta U, which in turn implies delta V, which is equal to weight of P, which is equal to weight of q plus UV, which is equal to weight of q plus weight of UV, and this is equal to delta U plus weight of UV. We have proved the theorem. So, what is the conclusion we get? The contrapositive of theorem 1, okay, and this theorem implies delta V is equal to minimum of delta U plus weight of UV. For every edge UV in E, if there is an incoming edge to V, consider delta U plus WUV, which is same as minimum over U belonging to V such that UV belongs to E. For each neighbor you compute delta U plus WUV and take the minimum, you get delta V. All right. It is a beautiful equation. We will do little bit of cleanup here and make it even simpler looking. Suppose we extend the weight function if an edge is not there, right. If an edge is not there, we said WUV equal to infinity, WUV equal to infinity if UV does not belong to E, U not equal to E. We will also set WUU equal to 0 for all U. This is extension of weight function. Your input graph has got edges. For each edge there is an weight associated with it. We mathematically extend it. If an edge is not there, for that pair we associate a weight infinity, and at every vertex UU, of course the graph does not have any self loop. So WUU is set to 0 and WUV equal to infinity if you. Under this definition, for any u this is true, because if UV is not there, WUV is infinity. Any quantity will be less than infinity anyway. Therefore, we can write this as delta V equal to minimum over U of delta U plus weight of course minimum. So, you compute this all U not equal to V, because V is on the left hand side. So, for every vertex compute for every vertex V, compute for all U1, U2, U3, you have delta U1 plus weight of U1V. Compute this, delta U2 plus weight of U2V and delta U3 plus weight of U3V and so on. Okay. If an edge is not there from a vertex U dash, this is anyway given infinity. So, every quantity is less than infinity anyway. In your actual computation you do not have to use that, but to simplify the notation by introducing VU dash is infinity. Anyway those quantities delta U dash plus weight of U dash V will be infinity. So, if an U dash is not adjacent, this quantity automatically becomes infinity and it will not affect the minimum. Anyway, compute these quantities and find minimum, then we get delta V. Okay. So, a very compact and a clean formula for the vertices in a graph delta V. Okay. Now, if the graph has got no negative cycle, what is delta S? What is the interpretation of delta? What is the meaning of delta? From S, the shortest path to S. Basically it is a closed path, which means it is a cycle. Okay. But all cycles have got 0 or positive 1. So, why go out of S? Stay in S. To reach S from S, do not move, right. If you go somewhere and come back to S, that is a path from S to S, but that is a cycle, but all cycles have positive or 0 weight. So, you do not have to do any calculation. We set delta S equal to 0 as all cycles are non-negative. There are no negative cycles. Therefore, we set delta S equal to 0. Therefore, in sum delta S equal to 0 and delta V equal to minimum over U not equal to V of delta U plus weight of UV, and this is an interesting relation between the input and output. Input values are the weight function values, output values we are looking for are the delta values. So, there is a functional equation set up between input values and the outputs you are looking for, right. These equations are known as Bellman equations. For shortest path weights. The shortest path weights satisfy this equation. Therefore, if you define a variable xv is a variable associated with the vertex v and form the equation. What is the equation you have to form? X of S equal to 0, x of v equal to minimum over u not equal to v of x of u plus weight of uv. These equations, right, are the abstract form of Bellman's equations. So, this is called Bellman equations for n variables. Given a graph, you can always write down these equations because the graph has got weight uv. For each edge there is a weight, for each vertex there is a mathematical variable. So, n variables and you write down these equations, you have Bellman equation. A solution for Bellman equation is the shortest path distances. We have shown that xv equal to delta v is a solution for the Bellman equations. We have shown that this is a solution for Bellman's equation, that is a good news. So, we have a mathematical equation whose solutions are the values we are looking for. We want to compute the shortest path distance. So, in order to compute, we can set up an equation and then we can attempt to solve that, and the solution for that is Bellman, solutions for that are the shortest path distance. Okay? Things look promising as of now. We are not there yet. We need to show one very important result. We may form the Bellman equation, but what if that equation has non-unique solutions? Delta V may be a solution, but if there are other values which are also solutions for them, after solving the equation you will get some values, but you do not know whether they stand for the shortest path distance or some junk numbers. So, we are going to put another very simple condition which will make these equations to have a unique solution, namely the shortest path distance. Now, we can attempt to solve the equation, because if we succeed, since the solution is unique and the solution is shortest path distance, we are going to obtain the shortest path distance. So, I state a theorem which is guaranteeing a unique solution for Bellman equation. It is a very simple extension. If G has no negative cycles or no zero cycles, then Bellman equation have a unique solution. We shall continue with our discussions on this aspect in our next session. Thank you.